Professor Wang. Dr. Zhangxin Wang is currently a professor in the Institute of Environmental and Ecological Engineering at Guangdong University of Technology. He obtained his PhD degree from Vanderbilt University and finished his postdoc training at Yale University. His research focuses on membrane waste treatment technologies and has published nearly 30 papers on the known journals such as Science Advances, Environmental Science and Technology Water Research. So
Okay.
let's enjoy Professor Wang's speech.
Thank Dr. Xia for the very nice introduction. I'm Zhangxin Wang from Guangdong University of Technology. The title of my talk today is Comparison of Osmotically-Assisted Reverse Osmosis and Low-Salt-Rejection Reverse Osmosis for Brine Management. Firstly, I'd like to give a brief introduction to the background. As is well known, freshwater scarcity has become a global issue. And due to the intensive industrial activities, a large amount of fresh water is turning to brines every day. If not appropriately treated, the discharge of the brine would further intensify freshwater scarcity. Therefore, zero liquid discharge, or ZLD, has been proposed as an ambitious brine management strategy. In current ZLD process, the wastewater is firstly pre-treated and then sent to an RO unit to recover the fresh water. And the brine from the RO unit is sent to a mechanical vapor compressor, or MVC, to further recover the fresh water. And the final brine is sent to a brine crystallizer to remove all the water and generate solid. However, the current ZLD process is still limited because the capital cost and the operational cost are both very high, mainly due to the use of the MVC. So to further advance the application of ZLD process, we propose two solutions. The first one is that we can develop novel RO technologies that can enhance brine concentration capability and lower the working load of MVC. And second one is that we can develop novel thermal brine concentrators to replace MVC. So in this talk, we will focus on the first solution, developing novel RO technologies. Here we want to have, I want to give you a brief introduction to the limitation of conventional RO in ZLD. We know that based on the working principle of RO, we have to have an operating pressure that is larger than the transmembrane osmotic pressure to drive the water flux. And in conventional RO, the product is almost fresh water, which has an osmotic pressure nearly to zero. Therefore, the transmembrane osmotic pressure difference is actually equal to the osmotic pressure of the brine. That is to say, in conventional RO, we need to have an operating pressure that is larger than the osmotic pressure of the brine. And we also know that the osmotic pressure of the brine increases with the brine concentration. And in conventional RO, the operating pressure is usually limited at 85 bar, which corresponds to a brine concentration of 1.4 mole as sodium chloride, or 80 grams per liter total dissolved solids. However, the brine inlet for the brine crystallizer is usually over 200 grams per liter TDS, or 4 mole as sodium chloride. Apparently, there is a huge gap between the two concentrations. Therefore, because of the since the maximum brine concentration of the conventional RO is restricted by the operating pressure, we have to extensively use MVC in ZLD. To overcome the pressure limitation of conventional RO, we have developed a novel stage RO technology using low-salt-rejection RO membranes, and we name it as RSRO. So here is the schematic of RSRO. In RSRO system, we use a conventional RO module with salt rejection close to 100% in the first stage, and low salt rejection RO modules in the consecutive stages. And during operation, in each low salt rejection stages, the brine is sent to the next stage for further concentration, and the salty permeate is cycled back to the previous stage for additional feed. And the working principle of RSRO is very simple. In the low salt rejection stages, the permeate is salty. The salty permeate can mediate the transmembrane osmotic pressure difference, thereby further concentrating the brine without elevating the operating pressure. Besides RSRO, there is another novel stage RO technology that can also highly concentrate the slant feeds without using a ultra high operating pressure, namely osmotically-assisted RO or OERO. So in an OERO system, a conventional RO module is used in the last stage, and the other stages are using countercurrent flow RO modules. So in each countercurrent flow RO module, there are two streams flowing countercurrently. One stream is a low salinity stream, and the other is a high salinity stream. Because the low salinity stream can mediate the transmembrane osmotic pressure difference, therefore, the high salinity stream can be further concentrated without using elevated operating pressure. Based on the working principles of OERO, the energy consumption in OERO is only dependent on the final brine concentration. So in this study, we compared RSRO and OERO in ZLD applications from 3 different perspectives. So firstly, we compared RSRO and OERO on brine concentration capability. So we plotted the maximum water recovery of conventional RO and two-stage OERO and RSRO with different feed concentrations. And we found that both OERO and RSRO, the gray columns, can increase the water recovery of the conventional RO, the blue columns. And compared to the conventional RO, the two-stage RSRO or OERO can reduce the brine volume by half. Therefore, in terms of brine concentration capability, OERO and RSRO are equally competitive. Then we compared RSRO and OERO on energy efficiency. We first plotted the specific energy consumption, or SEC, of 3-stage OERO and RSRO with different feed concentrations. And we found that when treating feed with relatively low salinities, RSRO is better than OERO. While when treating hypersaline feeds, OERO significantly outperforms RSRO. We also compared the SEC of 4-stage OERO and RSRO with different feed salinities to figure out the impact of stage number on the energy comparison. And we found that with four stages, the SEC of RSRO significantly decreases compared to that with 3 stages, while the SEC of OERO remain the same with varied stage numbers. Therefore, with more stages being used, RSRO would be more advantageous than OERO. We further compared RSRO and OERO with an elevated operating pressure. So we found that with the operating pressure increased from 80 bars to 120 bars, the SEC of RSRO significantly reduces the green columns, while the SEC of OERO still remains the same. Therefore, in the future, with our models that can withstand larger operating pressures being developed, RSRO would be more advantageous than OERO. Lastly, we compared RSRO and OERO on practicability. So in terms of module availability, OERO is using countercurrent RO modules. These kind of modules are few in market. In contrast, RSRO is using a conventional RO or NF modules, which are commercially available. In terms of capital cost, in the countercurrent RO modules used for OERO, the operating pressure cannot be large to avoid the channel deformation, which means that the water flux cannot be very large. Furthermore, with the water permeation from the across the membrane, there would be severe concentration polarization effect, which would further reduce the water flux. While in RSRO, a large operating pressure can be applied, and also because of the salt permeance from across the membrane, the concentration polarization effect will also be mitigated. Therefore, in terms of water flux, RSRO is better than OERO, which means that in RSRO systems, fewer modules are required compared to that in OERO system. In addition, compared with OERO, RSRO demands fewer high pressure pumps and energy carry devices. Therefore, in terms of capital cost, RSRO is more advantageous than OERO. In conclusion, in this study, we made a comprehensive comparison between RSRO and OERO. And we found that in terms of capability, both RSRO and OERO can highly concentrate the sealant feeds without elevating the operating pressure. While in terms of energy efficiency, RSRO is more advantageous than OERO when treating feeds with relatively low salinity. While for treating feeds with high salinity, for hypersaline feed treatment, OERO would outperform RSRO. However, with more stages being used and/or elevated operating pressure, RSRO will outperform OERO in the future. In terms of practicability, the membrane modules for RSRO are commercially available, and the capital cost of RSRO should also be lower than that of OERO. Therefore, in summary, RSRO is a more promising technology for brine management compared to OERO. With this, I want to thank my postdoc advisor, Manny, and all the collaborators, as well as the funding agencies. Thank you all for listening. I'd like to take any questions you may have.
Yeah, Professor Wang, I have one question for you.
Sure.
In the LSRO, since you have multi-stages, for each stage, will you use different type of membrane? And have you tried the commercial membranes, or will you develop your own membrane?
Yeah, thanks, Dr. Xia, for this very nice question. Yes, we need to have, because of the time limitation, I didn't go into the details of our study. Yes, we need to have different membranes in each stage. We need to do some optimization for the regarding the salt rejection in each stage. And currently, this work is still a theoretical work. It is done by modeling. We haven't done a lot of experiments. So I think, and now we are trying to do some experiment with the commercial nanofiltration membranes and also some brackish RO membranes. And I think we can also adjust the salt rejection using some chemical treatment to achieve the optimized salt rejection for each stage.
Okay, thanks a lot for your great answer.
Dr. Xia, I have a question to Dr. Wang. Okay.
Sure.
Yeah. I can read it in my text. It was very nice work and very smart actually. But I just wonder, do you have any assumptions in your calculation, in your model, which may have some negative impact to your capital cost and operational cost? My understanding is that when you add an extra stage, the capital cost will take a significant part of the total cost, which has to be depreciated by operational cost. So I'm a bit concerned about this. Can you comment on this? Thank you.
Yeah, sure, Professor He. It's a very interesting question. Yes, I think definitely if we have more stages, the capital cost will be higher. But unfortunately, we haven't done the very detailed cost analysis yet. But I think we will do it in the future. But I think the question you ask really depends on the trade-off between the operational cost and the capital cost. Because although although the more stages will increase the capital cost, it may also reduce the operational cost. So we need to find a balance with a more detailed techno-economical analysis. And regarding the assumptions, yes, we made some assumptions in the calculations. For example, we use Van Hoff estimation to calculate the osmotic pressure, and also we made some because for this work we use process modeling, and we just use some very simple equations based on the RO working principles. But we are now trying to do more like comprehensive work, a more detailed work with model scale analysis. And the results are a little bit different from what we got here, but the trend is still the same.
Thank you, Dr. Wang. Very nice answer. Thank you.
Thank you for the question.